the 10th webinar in our series. My name is Tim Dixon and I'm here to introduce Yasmin Kemper, who will be presenting today on some work that we've done on emissions accounting for CO2 enhanced oil recovery. This is obviously quite an interesting topic. It's quite topical and we look to do things that people haven't done before, so the work that's been done here has tried to build upon work that others have done, and in the process we discovered the complexities around topics, and that's certainly true for this case, for this study here. Just a quick introduction to ourselves. Moving on to the next slide. The IEA Greenhouse Gas R&D program, we were part of the International Energy Agency family, been so since 1991. So we're part of the Energy Technology Network, and we're one of the technology cooperation programs within that. And our remit is to undertake research on the role of technologies to reduce greenhouse gas emissions from the use of fossil fuels. We've got in total 32 members from 18 countries plus OPEC, EU, the Coal Industry Advisory Board, plus other companies and institutions. And our members set the technical program, the topics and the direction of that. We are an R&D organisation, so we don't prescribe on policy, and so we may be policy relevant but not policy prescriptive. And we're not advocates of any one technology, but the nature of our work looking at reducing greenhouse gas emissions from the use of fossil fuels does mean that we tend to focus on carbon dioxide capture and storage. So what we do is assess the options for reducing greenhouse gas emissions, focusing on CCS in particular. We track development in capture technologies, and the costs and developments around those, technologies and knowledge around the understanding on geological storage of CO2, the monitoring technology, storage performance, risk assessment, modelling, etc. And we aim to provide our members and a policy audience with independent technical input. All of our reports are externally peer reviewed, and so that we can be assured of the integrity of the work when we input to bodies such as the UNFCCC, ISO, London Convention, and other forums such as that. And that's our membership base. The countries representing developed and developing, and the institutions and companies representing many sectors of industry and economic activity. So that gives us a very good input to our technical program. Very pleased to introduce Yasmin Kemper, Dr. Yasmin Kemper. She has been with IEAGHG since 2011, a chemical engineer by background with a PhD in chemical engineering on the evaluation of amine-based solvents, and Yasmin has impressively broadened out from that topic to cover for us topics such as bio-CCS, CCS clusters, life cycle emissions, and non-CO2 greenhouse gases, and CO2 utilisation. Yasmin's already presented on the bio-CCS webinar, and I'll hand over, it gives me great pleasure now to hand over to Yasmin to present to us today on emissions accounting for CO2 EOR. Thank you, Yasmin.
Thank you, Tim, for the introduction, and first of all, welcome to everyone who's tuned in to follow our webinar on CO2 enhanced oil recovery. So first of all, I want to give you a quick overview of what you can expect in the next couple of minutes. And there have been quite a lot of reports already been done on various aspects of CO2 enhanced oil recovery. And there were especially two reports which caught our attention, and which I will briefly present here before introducing our own work. That's one report done by the Pembina Institute in Canada, and also one report done by our mothership, the IEA in Paris. And And I first start with the Pembina report, and also on first note, I won't have time, unfortunately, to explain in detail what CO2 EOR technically is. So we assume you're already a bit familiar with what CO2 enhanced oil recovery is about. And yeah, the Pembina report was issued in 2030 and prepared for Canada's integrated CO2 network. And the aim of that report was to better understand the greenhouse gas impact of CO2 EOR. And I'm also using a couple of abbreviations for the webinar. If you're not so familiar with them, we also have a handout with a glossary, so please refer to that if you want to look up any or clarify any abbreviations. And coming back to the Pembina report, they had two specific objectives in mind. That was quantifying GHG emissions from CO2 EOR, and also to support or to kickstart a more broader discussion on the topic. And yeah, the analysis uses actual operational data from a single Western Canadian site. And when regarding the methodology used in the study, it adheres somehow to ISO 14064, but the authors also mention that they do not strictly follow all procedural requirements. So the next slide gives you an overview about the scenarios that the authors chose in the study. So they have scenario number 1, which is the reference scenario and which represents pure geological storage. And then scenario number 2, which just considers the net storage through enhanced oil recovery on site. And then the more interesting scenarios 3, 4, and 5. Scenario 3 then takes into account the EOR full lifetime emissions. That means including emissions from production activities, transport and refining, and also combustion of the end product. Scenarios 4 and 5 then are a further step off, and in those scenarios the authors actually considered an offset. One case against an oil sands barrel and the other case against an average barrel in the market. So what the study found out is, and you can see that on this slide, which shows you the GHG emissions in tons of CO2 equivalent per ton brought to the site for those different scenarios. And you can see that the first scenario, which is the pure geological storage scenario, would lead to almost all of the CO2 brought to site being stored in information. And for the EOR side, there are different numbers out there, and for this particular site, the authors found that approximately around 70% of the CO2 used for EOR would be stored in the oil field when used for enhanced oil recovery. So those cases provide the baseline, and then you can see the results for scenarios 3. That means taking into account the production and combustion and the whole life cycle emissions, and that would then bring you up from kind of a negative net emissions to positive net emissions. So you would see that that all those on-site and downstream emissions kind of outweigh the storage emissions. Then for the two scenarios, oil sands displacement and average barrel displacement, you could see that if you would assume that full displacement of these sources would occur, you would end up with quite large net negative emissions, so a very beneficial aspect then of these activities. So on the next slide, you see again similar results, GHG emissions for the, apologies, can you go back? GHG emissions for the different scenarios. And you see again on the left side those two reference cases, just for information. And then you can see that for the other three cases, the authors did a kind of sensitivity analysis to the oil field productivity. And you can see that from all the three columns in each case, the one on the left side is for a productivity of 1 barrel per ton of CO2 injected, and then step-off cases for 3 and 5 barrels per ton of CO2. And this is because although the study mainly focused or used those 1 barrels per ton of CO2, this is not really a representable oil field productivity, so the authors also wanted to investigate what would be the case if productivity would ramp up. And what you can see for the on-site and downstream emissions is that as field productivity goes up, also so do the emissions. And only in case that you would then offset these emissions, you could then end up with, again, negative emissions. So on the next slide, I've summarized the main conclusions from the report. So it's very important to take in mind that site-specific factors make a generalization about GHG performance of CO2 EOR in general very difficult. So the study done was done on actual field data, and of course then only apply to that site. And other EOR sites might be very different. It was also found that usually geological storage provides the more significant greenhouse gas benefits, and because in this case you also do not have to deal with all those downstream issues and all those issues around what displacement you can assume. Are you going to displace an oil sands barrel or rather the average barrel? And another finding was that also that the carbon intensity of oil from this specific EOR site would fall somewhere between the Canadian oil sands and US average barrel. So of course, if you have an oil that falls somewhere in between, it would then not make sense to maybe put that on the market that is mainly consistent of US average barrels. And also a very important takeaway message that the performance ratio has a very large impact on the overall GHG performance of an EOR operation. And thus the impact of storing CO2 through EOR varies greatly depending on the perspective that you take. And also this is not meant as a criticism, some limitations of the report, and a lot of those limitations were also raised by the authors themselves. They again emphasize it's a site-specific analysis, and also that the scenarios assume either no or full displacement, that means substitution in the market, in the oil market, and also taking into account that the site data, the underlying data was for a performance ratio of 1 barrel per ton of CO2, which is considered well below industry average, and that, as we have seen in the results slide, higher ratios could lead to significantly higher GHG emissions if not fully offset against other carbon-intensive sources. The study also assumed what is quite unlikely, that the EOR performance would be fixed in time, but this was due to data limitations, because the data they had available was only for a certain short period of time. Also, there was no consideration or discussion about CO2 credits and allocation of CO2 credits along the EOR chain, and thus no particular views on the appropriateness of the different approaches and scenarios investigated. So now we will move on to another report, which was published just at the end of last year by the IEA in their Insight series. And this was work mainly carried out by some of our colleagues from the IEA CCS units. That's Wolf Haiduk, Juho Lipponen, Sean McCoy, but also from the energy team, which is Philippe Benoit. And they investigated storing CO2 through enhanced oil recovery. And the main driver behind the study was to look for win-win situations for business and climate change mitigation goals. And the study set out under the assumption that CO2 EOR can be modified to deliver significant long-term CO2 storage. And for this, some additional requirements would need to take place. That is additional site characterization and risk assessment, additional monitoring of vented, fugitive and subsurface emissions, and also a review of field abandonment practices. And their analysis was based on a hypothetical but representative field. So the study proposed 3 different EOR plus models. They call it EOR plus because it would be a step off or a bit different in terms of technology and requirements from standard industry EOR practices. So there is the conventional EOR plus, which would be based on the current EOR practices, maximizing oil production, but also taking into account additional monitoring and verification required for the CO2 stored. Then there's the advanced EOR plus case, which would try to co-exploit oil production and CO2 storage for profit, and which would have a higher CO2 injection and oil recovery than the conventional EOR plus case. And then the third case is the maximum storage EOR plus model, in which the focus would be on maximizing the long-term CO2 storage, but at the same time achieving the same level of oil production as the advanced EOR plus case. And this slide shows you some of the results, and it shows you the global storage potential for the different models in gigatons of CO2. And on the right side you have a comparison of the cumulative CO2 storage under the 2 degrees C scenario. And you can see that especially the advanced and maximum storage EOR would or could deliver significantly higher storage potentials than would be needed to meet that scenario, and also already the conventional EOR plus scenario would deliver a significant amount. So if we look a bit further into the results of that studies regarding the emissions at the project level, the CO2 stored is offset by direct and indirect emissions, which can be significant. We have already seen that in the Pembina results as well. And for all 3 scenarios, the study found that the project level emissions would be negative, but only for the case that you would use CO2 from anthropogenic sources, such as from CCS operations, from CO2 capture. And if you would use CO2 from a natural source, then no emissions reductions benefit would accrue. The study then looked at emissions taking into account the consumption of the oil. And in the first case, looking at that no displacement occurs, and that in that case all oil would be additional. And in those cases, the advanced and maximum storage EOR plus cases would still lead to emissions reductions, mainly due to the increased amount of CO2 stored per barrel. And then in a third step, looking at the emissions from EOR operations with displacement of oil, and also reminding that there is a wide range of crude oil intensities. And so there's also a wide range of potential benefits depending on the chosen offset. We have also seen that's in line with the Pembina results. And that investigation found that all EOR plus scenarios could lead to emissions reductions until a displacement rate of around 50% is reached. And again, the advanced and maximum storage EOR plus scenarios show a large benefit, or a larger benefit as the conventional, case, as they already resulted in reductions without considering the displacement. So the conclusions from this IEA study is that also storing captured CO2 in saline aquifers would be more effective for reducing atmospheric emissions, but that co-exploiting recovery and storage can lead to significantly higher net present values. I haven't shown that results because I was more focusing on the greenhouse gas effects, but that's also in the report if you are interested in that information. And that emissions reductions and economics are ultimately project specific, that implementing those proposed EOR plus technologies would need a paradigm shift in the EOR industry, because there are additional requirements. Also, you would need pilot projects, incentives, regulatory and legal frameworks would need to be amended, and so on. So now we'll go over to present the results of the study that IEAGHG commissioned. We commissioned this study to Carbon Counts, to Paul Skoor and Greg Cook. And they looked a bit deeper for us into the topic of emissions accounting for CO2 EOR. And this report is forthcoming, and we aim to publish that within the next 6 to 8 weeks, approximately. And this study was following on especially from the Pembina Report and some of the open questions it left. And also acknowledging that CO2 EOR is an early opportunity for a CCS demonstration, because it can offer the opportunity to partially offset CCS costs through the incrementally produced oil. And but that there might also be a conflict. So you have the GHG reductions through the storage, but you might also have further downstream additional emissions from increased oil use. So the key issue was seen as how to account for and reward climate benefits from these operations. And yeah, we found the need to review those GHG accounting issues surrounding the EOR operations. So when we look at those accounting issues, we have one concept emerging, which we call emissions leakage, and I'm providing you the definition for emissions leakage on this slide. So emissions leakage means the potential for net changes in emissions to occur outside the boundaries and operational control of a particular policy or activity, but arising as the consequence of this policy or activity. And this description is compliant with the Kyoto Protocol's clean development mechanism. And yeah, this concept can potentially undermine the environmental integrity in cases where GHG incentives would apply. And in the context of CO2 EOR, that means emissions leakage could occur in absence of GHG policies and measures. And it's could be quite likely to occur where the incrementally produced oil would add to our overall supply. So in case it would be additional and no substitution or displacement would occur. And in the case where the IPO would actually substitute products with higher emissions intensity, such for example as oil sands, which are very emissions intensive, you could end up with an actual reduction in net emissions, and that's where a lot of studies were also taking out, putting out the claim of carbon negative oil or green oil under that assumption. And yeah, the scope of work for this study included the following. So the main objectives were to review the GHG accounting and monitoring, reporting and verification rules for CCS projects that involve CO2 EOR. Also to maybe have a quick look at developing a first-party methodology on how you could calculate that risk or estimate that risk. The focus hereby was on whether and when to account for the mid and downstream emissions of the IPO, and also how to account for these emissions. And I've put here quantification, but please be aware it's not quantification like a quantification in the, for example, Pembina report that we actually calculated these emissions. It was more meant in developing or discussing how you at best could quantify those emissions. So to be clear, this report will not consider any upstream emissions that take part before the CO2 arrives at the EOR site, and also not a detailed life cycle assessment across the whole chain of the CO2 EOR operation. We had some key assumptions to assess the risk of emissions leakage, and that was that an incentive for CCS already exists and that all site-level emissions are accounted for or covered by policies, and that where GHG emission controls are asymmetric, the emissions leakage risk would increase, and in that case the IPO would likely add to overall supply. But where you would have controls in place that cover the whole value chain, you can assume that the risk would decrease, and because the IPO would very likely substitute supply from other sources. And yeah, from this it follows that if you have sufficiently wide boundaries, you can pretty much reduce or eliminate that risk for emissions leakage. So this is just a graphic explaining what we understand under upstream, midstream and downstream emissions. And the definitions are quite a bit different from maybe what standard oil and gas sectors understand. So for us, upstream is anything before the CO2 arrives at the EOR site. So this includes emissions from fuel supply and also any emissions that are related to the CO2 capture activity. Then we have the on-site emissions for CO2 storage and or EOR. And there you have quite a range of emission sources where CO2 can come from. For example, venting and flaring or fuel use for the activities and so on. Then we have the midstream part. So as soon as the produced oil leaves the gate, you might have transportation to other places, which would incur emissions from shipping or other transport. Then you could have additional emissions from the refining steps. And then it could also occur that, for example, the products or the oil are further transported to their final destination of end use. And then, of course, you also have the emissions from the end use itself. So if we now have a look at the upstream emissions, I clarified that we are not taking that into account because most GHG regulations already allow captured and exported CO2 to be deducted from a facility's GHG inventory. And those, for example, include the IPCC guidelines, the EU ETS, or the US Greenhouse Gas Reporting Program. And it already provides the basis for carbon price incentives. And yeah, we generally do not see many issues here. And also we do not see many issues for the site-level emissions because usually all GHG policies supporting CCS require monitoring of those site-level emissions. For example, surface energy use, vents, flare, and other fugitives, or reservoir seepage. Now, where we think it gets interesting is the mid and downstream section, because these emissions may or may not fall within the scheme's boundary, because we have transboundary movements. And so, yeah, whether you can track or account for these emissions depends on the movement of the crude oil across borders. And because you might transport the crude or the product into jurisdictions where there is no counting, you might end up with the emissions leakage that we defined earlier. Yeah, this slide just goes into a bit more detail about the substitution and addition, and yeah, just explains the difference, which should be quite clear. If you have substitution, then your CO2 EOR supply goes into the market, and you have restrained consumption, and so the the risk of this emissions leakage is lower because you actually substitute or replace oil that's on the market. However, if you just add to the overall supply, you can then see you might end up with unrestrained consumptions, and then you actually put more oil on the market and also cause more emissions in the end. So the total emissions the total consumption just increases. So what the study now did was it used GHG policies and measures, that's PAMs, to indicate the risk of emissions leakage. So you usually have a low risk of emissions leakage where, for example, refining is subject to the emissions controls, and also where the end use is subject to constraints, for example, through portfolio standards for vehicles, for fuel suppliers, or, for example, sector controls for the aviation sector. And in that case, you are, you can pretty much assume that substitution would occur. However, there are also cases where you have a higher risk for emissions leakage, and that is where you have weak policies or no policies at all in place. And then, you have a scope for unconstrained increase in fossil fuel use. And in some cases, you might even have subsidies on fossil fuel consumption that could encourage growth of fossil fuel use. And then you are very likely to add to overall supply. But we are aware that those policy measures may not be a perfect risk proxy, because there are variations in the stringency of GHG policy and measures. For example, a variation in the Kyoto Protocol and INDC targets, and also variations in national policy and measures. And I put an example, for example, EU vehicle standards and US vehicle standards, and you can see that the timelines and also the actual amounts for CO2 emissions are quite a bit different. And then, of course, it becomes very challenging to consider, that in the overall discussion or determination of the CO2 emissions from those EOR operations, especially for the mid and downstream part. And also there's a wide range of other factors at play. There are oil price dynamics, there might be subsidies on production and consumptions and other political interventions, and that adds even more to the complexity of this topic. So now a bit more on whether and when to account for emissions leakage. So the current patchwork of GHG policy and measures can drive different types of emissions leakage. So you might have a transboundary emissions leakage or also cross-sectoral emissions leakage. And also the risk for this to occur is variable due to the, as I mentioned before, the variations in type and stringency of GHG control schemes. And the risk also depends on the characteristics of the global oil market, on global oil production, supply, and end use. And also to be very mindful, even if economy-wide controls and reporting obligations are in place, you are still never 100% sure that emissions leakage could not occur. So the study then looked into how to account for this emissions leakage and found it necessary to develop an emissions factor reflecting the mid and downstream emissions from IPO. And those estimations would be based on emissions intensity per barrel across the value chain. Then a second pillar that you need to take into account is the degree of emissions leakage. And as I've explained on the earlier slide, you might even be able to have a kind of negative emissions leakage. So you actually substitute a more emissions intensive source and then end up with beneficial gains for climate change mitigation. But this depends on whether and to what extent substitution occurs. And we have already, I think, stressed it a couple of times that that determination is really challenging. And overall, there are three approaches to estimate that emissions leakage risk. You could do a project or product specific approach. one considering marginal supply, or one being based on market average. And and explaining a bit on what the study also proposed or looked into as a kind of first pass method on how to estimate that risk, and that will be in the report if you are interested in that. And it's also important to take in mind that it's just a proposal, so we do not see it as a verified method that anyone should use to now actually go out there and do that calculations. It's more meant to start discussions on it, and it needs further improvement in the future, because there are limitations that apply to the approach that we developed, and that's lack of high quality data. It's also, if you develop such an approach, you have to keep the data up to date, otherwise your approach is, after a couple of years, becomes outdated and useless. And also the measurement and attribution of substitution is not straightforward. And there are also equity issues, such as the disparities between inventory quality and reporting of crude oil extraction and refining emissions. And it would also be quite challenging to implement in practice to all the related complexities of the topic. So now to come to the conclusions. Again, the most important conclusion for me is the topic is very complex, but we can also draw out some helpful conclusions. So where the incrementally produced oil adds to the overall supply, emissions leakage can occur. However, when the incrementally produced oil substitutes supply with higher emissions intensity, we don't think emissions leakage will occur. And we also found, or study found, that the stringency of GHG control schemes can be a first proxy for measuring or estimating that emissions leakage risk. And we're also convinced that the emissions leakage risk is material but also variable because of the different and more or less significant emissions from end-use extraction and refining. And what's a big thing to keep in mind, and that needs further investigation in the future, is whether the IPO causes substitution or addition, or what then the substitution rate would be if you can assume substitution. And we also end up with some recommendations from our work, and that is that we see a need for further discussion to identify the full range of issues surrounding possible emissions leakage from CO2 EOR. We think it would be useful maybe to take the proposed approach and to test it and in real world setting, and then to maybe come back and refine it, or maybe you find out it's too complex to actually propose a methodology. And due also to the complex topic, we think there are a lot of studies out there with a lot of claims. You need to be careful and mindful in extracting and communicating the findings, because a lot of the studies are very site-specific, so you really can't just transfer general conclusions from that. And with this, I would like to finish my webinar. Thank you for your attention and keeping up until the end. And if you have any questions, then we will try to address them now, or we will also collect your questions and then come back with you in due time with the answers.
Okay, thank you very much, Yasmin. And just while you draw breath,
thank you.
Just to some people have asked about the availability of the PowerPoints and the webinar afterwards. There will be a recording made of this.
Yes.
And we'll make that available on our IEAGHG YouTube channel afterwards. We also had a question relating to the IEA CCS unit report about the max CO2 EOR scenario, whether that exceeds the original reservoir pressure. And that maximum CO2 EOR scenario does a once-through system where the produced water and the produced CO2 is actually put somewhere else afterwards into something like the stack storage concept. It's not put back into the same reservoir. So Yasmin, we've got a couple of questions that are related. One in the sort of question looking at the upstream emissions and the energy penalty and transport leakage, and how the production emissions relate and compare to the combustion and usage emissions.
Yes, our study had a short discussion on that included in one of the chapters, and actually draw upon very good work done by the US DOE National Energy Technology Laboratory, and they did assessments of the well-to-wheels GHG emissions for a variety of crude resources. And from that analysis you can see that it really depends on the crude source, and there is a variation of, I think, up to around 25% due to the differences in especially extraction and refining of the crude. They also give the share for the crude oil transport and the finished fuel transport. Those emissions are more on the lower side. I think they don't make up more than maximum 3% of the total emissions, so are more on the insignificant side. So it's more the extraction and refining that can differ, especially the extraction, and that can cause very different emissions. I think on the higher side they had Venezuelan upgraded bitumen, and on the lower side Algerian or UK domestic crude oil. So that's in our report, so if you're interested you can go back to the source of NETL and then extract the information.
Okay. A question, the study is looking at CO2, but there's also methane emissions from these activities. The reason for focusing on CO2?
The reason for first focusing on CO2 is that once you also then start to look at methane emissions at the same time, I think methane emissions is also a topic worth on its own to consider. And we have some watching briefs on methane emissions, which we will attend to in the future. And also taking into account that already a lot of US institutions do work on methane emissions, but it's definitely a very important topic to also consider.
Okay. A question around the life cycle balance and just the source of the CO2, how significant is that? And the example in the question is between a CO2 from a coal power station compared to CO2 from a fertilizer plant.
Yeah, I mean that's what I also mentioned in the beginning. We didn't consider any upstream implications in that study, so that was out of scope. But it's definitely a valid and important point, because there are also already studies and assessments out there, for example, taking into account the different sources, especially if the CO2 comes from biogenic emissions. So you have maybe a biomass corn ethanol fermentation plant, and then using that, and because you have the, for biomass you usually have the carbon neutrality assumption, because the biomass grows, and so if you emit it you just end up carbon neutral, and then if you rather take the CO2 to store it in CO2 EOR operations, you end up with what is called carbon negative oil or green oil. So it will definitely have an impact in the accounting where your CO2 comes from, whether it's biogenic or fossil.
Okay, thanks, Yasmin. Another question relating to the US system of greenhouse gas reporting and their subpart RR, where they report from geological storage. How does this relate to that? And I think that's the subpart RR is a project-based, and the boundary would be the project-based boundary. And this study is looking and adding in what happens when the products go outside of the project boundary. Do you have any comments on the relevance of the US system and this study to the US system?
I'm thinking, I'm just remembering.
So I think that these are a set of rules that are specific to the storage side, the injection side, that can be also applied to a CO2 EOR site. So they're very much the project-based.
I'm just aware that there is currently a project, the Oxy Denver unit, that's falling under the subpart RR, and they have proposed a monitoring, reporting and verification plan, which has been approved by the
EPA.
By the EPA, And the thing generally, I mean, it's generally an issue or a question. If you look, I mean, you can have two viewpoints when looking at the CO2 EOR operations. You can try to have a whole life cycle approach where you really look from the beginning to the end. What are the emissions? What are the implications? What are the responsibilities along the chain between operators and consumers? Or you can also say you look in isolation or in separation, for example, at the site level emissions, because you could argue, the EOR operator is not responsible about consumers using or wanting more oil. So it's a difficult question to answer.
What's required from the subpart RR requirements. So another question, I think this will be the last question now because of the time. But this was to do with the emissions leakage, that it could be quite material from CO2 EOR. Do you have a range of factors that you're thinking about, and how do we determine materiality of the emissions leakage? And do we know the emissions leakage in relation to the stage of the process?
Well,
it's quite a general.
It's quite general, but
question.
Our contractors looked into that about the likelihood and scale of emissions leakage. That's also in the report. So they analyzed the global oil and refined product trade flows, and they found that it seems there are some hotspots. So hotspot means you have large oil flows, and you also have a high risk of emissions leakage. And of course, high risk of emissions leakage in our report was meant we used the GHG, the stringency of GHG policies as a measure for this. And then you can see hotspots where you have large flows going in or out from jurisdictions which do not have any or just weak or poorly implemented control schemes in place. And that analysis looked at that at worst case, around 50% of the flows could be at a high risk of emissions leakage. And this would then equate to emissions of maybe around 4.2 billion tons of CO2, if you would assume the worst case. So that quantification was done in the report.
Okay. All right, Yasmin, thank you very much. We've got quite a lot of questions still coming in, and they look like questions that will take some answering longer than the time we've actually got. So to everybody whose questions we've not addressed yet, we will respond in writing to those and send those out. With that, I'll draw this to a close. Thank you very much, everybody, for listening and for the good questions. We've got a good number of questions in there and the good nature of questions as well. Yasmin, thank you very much for presenting and tackling this challenging and complex topic. And thanks also to the contractors, Paul Sikor and Greg Cook, who did the underlying work as well, and to the others involved in the other two studies that you've drawn upon. So with that, I'd like to draw this to a close and say thank you very much, Yasmin, and thanks to everybody for listening. Goodbye.
Goodbye.